In computing, an optical disk drive is a disk drive that uses laser light or electromagnetic waves within or near the visible light spectrum as part of the process of reading or writing data to or from optical disks. Some drives can only read from disks, but recent drives are commonly both readers and recorders, also called burners or writers. Compact disks, DVDs, and Blu-ray discs are common types of optical media which can be read and recorded by such drives. Optical drive is the generic name. Drives are usually described as CD, DVD, or Blu-ray, followed by drive, writer, etc. Optical disc drives are an integral part of standalone consumer appliances such as CD players, DVD players and DVD recorders. They are also very commonly used in computers to read software and consumer media distributed on disk, and to record disks for archival and data exchange purposes. Floppy disk drives, with capacity of 1.44 MB, have been made obsolete. Optical media are cheap and have vastly higher capacity to handle the large files used since the days of floppy disks, and the vast majority of computers and much consumer entertainment hardware have optical writers. USB flash drives, high capacity, small, and inexpensive, are suitable where read-write capability is required. Disk recording is restricted to storing files playable on consumer appliances, relatively small volumes of data for local use, and data for distribution, but only on a small scale. Mass-producing large numbers of identical disks is cheaper and faster than individual recording. Optical disks are used to back up relatively small volumes of data, but backing up of entire hard drives, as of 2011 typically containing many hundreds of gigabytes, is less practical than with the smaller capacities available previously. Large backups are often made on external hard drives, as their price has dropped to a level making this viable. In professional environments, magnetic tape drives are also used. History: the first laser disc, demonstrated in 1972, was the LaserVision 12-inch video disc. The video signal was stored as an analog format like a video cassette. The first digitally recorded optical disc was a 5-inch audio compact disc in a read-only format created by Philips and Sony in 1975. 5 years later, the same two companies introduced a digital storage solution for computers using this same CD size called a CD-ROM. Not until 1987 did Sony demonstrate the erasable and rewritable 5.25-inch optical drive. Key components: laser and optics. The most important part of an optical disc drive is an optical path, placed in a pickup head, usually consisting of semiconductor laser, a lens for guiding the laser beam, and photodiodes detecting the light reflection from disc's surface. Initially, CD lasers with a wavelength of 780 nm were used, being within infrared range. For DVDs, the wavelength was reduced to 650 nm, and the wavelength for Blu-ray disc was reduced to 405 nm. Two main servo mechanisms are used, the first one to maintain a correct distance between lens and disc, and ensure the laser beam is focused on a small laser spot on the disc. The second servo moves ahead along the disc's radius, keeping the beam on a groove, a continuous spiral data path. On read-only media, during the manufacturing process the groove, made of pits, is pressed on a flat surface, called land. Because the depth of the pits is approximately 1/4 to 1/6 of the laser's wavelength, the reflected beam's phase is shifted in relation to the incoming reading beam, causing mutual destructive interference and reducing the reflected beam's intensity. This is detected by photodiodes that outputs electrical signals. A recorder encodes data onto a recordable CDR, DVD-R, DVD+R, or BDR disc by selectively heating parts of an organic dye layer with a laser. This changes the reflectivity of the dye, thereby creating marks that can be read like the pits and lands on pressed discs. For recordable discs, the process is permanent and the media can be written to only once. While the reading laser is usually not stronger than 5 megawatts, the writing laser is considerably more powerful. The higher writing speed, the less time a laser has to heat a point on the media, thus its power has to increase proportionally. DVD burners lasers often peak at about 200 megawatt either in continuous wave and pulses, although some have been driven up to 400 MW before the diode fails. For rewritable CD-RW, DVD-RW, DVD plus RW, DVD-RAM, or BDRE media, the laser is used to melt a crystalline metal alloy in the recording layer of the disc. Depending on the amount of power applied, the substance may be allowed to melt back into crystalline form or left in an amorphous form, enabling marks of varying reflectivity to be created. Double-sided media may be used, but they are not easily accessed with a standard drive, as they must be physically turned over to access the data on the other side. Double-layer media have two independent data layers separated by a semi-reflective layer. Both layers are accessible from the same side, but require the optics to change the laser's focus. Traditional single-layer writable media are produced with a spiral groove molded in the protective polycarbonate layer, to lead and synchronize the speed of recording head. Double-layered writable media have a first polycarbonate layer with a groove, a first data layer, a semi-reflective layer, a second polycarbonate layer with another groove, and a second data layer. The first groove spiral usually starts on the inner edge and extends outwards, while the second groove starts on the outer edge and extends inwards. Some drives support Hewlett-Packard's LightScribe photothermal printing technology for labeling specially coated disks. Rotational mechanism. The rotational mechanism in an optical drive differs considerably from that of a hard disk drives, in that the latter keeps a constant angular velocity, in other words a constant number of revolutions per minute. With CAV, a higher throughput is generally achievable at the outer disk compared to the inner. On the other hand, optical drives were developed with an assumption of achieving a constant throughput, in CD drives initially equal to 150 kbps. It was a feature important for streaming audio data that always tend to require a constant bit rate. But to ensure no disk capacity was wasted, a head had to transfer data at a maximum linear rate at all times too, without slowing on the outer rim of disk. This led to optical drives until recently operating with a constant linear velocity. The spiral groove of the disk passed under its head at a constant speed. The implication of CLV, as opposed to CAV, is that disk angular velocity is no longer constant, and the spindle motor needed to be designed to vary its speed from between 200 rpms on the outer rim and 500 rpms on the inner. Later CD drives kept the CLV paradigm, but evolved to achieve higher rotational speeds, popularly described in multiples of a base speed. As a result, a 4A drive, for instance, would rotate at 800, 2000 rpm, while transferring data steadily at 600 kbps, which is equal to 4A, 150 kbps. For DVDs, base or 1A, speed is 1.385 megabytes per second, equal to 1.32 mbps, approximately 9 times faster than the CD base speed. For Blu-ray drives, base speed is 6.74 megabytes per second, equal to 6.43 mbps. Because keeping a constant transfer rate for the whole disk is not so important in most contemporary CD uses, a pure CLV approach had to be abandoned to keep the rotational speed of the disk safely low while maximizing data rate. Some drives work in a partial CLV scheme, by switching from CLV to CAV only when a rotational limit is reached. But switching to CAV requires considerable changes in hardware design, so instead most drives use the zoned constant linear velocity scheme. This divides the disk into several zones, each having its own constant linear velocity. A ZCLV recorder rated at 52A, for example, would write at 20A on the innermost zone and then progressively increase the speed in several discrete steps up to 52A at the outer rim. Without higher rotational speeds, increased read performance may be attainable by simultaneously reading more than one point of a data groove, but drives with such mechanisms are more expensive, less compatible, and very uncommon. Limit. Both DVDs and CDs have been known to explode when damaged and/or spun at excessive speed. This imposes a constraint on the maximum speed at which drives can operate. Loading mechanisms. Current optical drives use either a tray loading mechanism, where the disk is loaded onto a motorized or manually operated tray, or a slot loading mechanism, where the disk is slid into a slot and drawn in by motorized rollers. The motorized tray drives have the disadvantage of only being able to be opened and closed while the computer is turned on. If a CD or DVD is left in the drive after the computer is turned off, the disk cannot be ejected using the normal eject button on the drive. Most of these drives account for this situation by providing a small hole that one can insert a straightened paper clip or an ODDET to manually open the drive tray to retrieve the disk. Slot-loading drives have the disadvantage that they cannot usually accept the smaller 80mm disks or any non-standard sizes. However, the Nintendo Wii, because of backwards compatibility with Nintendo GameCube games, and PlayStation 3 video game consoles seem to have defeated this problem, for they are able to load standard-sized DVDs and 80-on disks in the same slot-loading drive. A small number of drive models, mostly compact portable units, have a top-loading mechanism where the drive lid is opened upwards and the disk is placed directly onto the spindle. These sometimes have the advantage of using spring-loaded ball bearings to hold the disk in place, minimizing damage to the disk if the drive is moved while it is spun up. Some early CD-ROM drives used a mechanism where CDs had to be inserted into special cartridges or caddies, somewhat similar in appearance to a 3.5 inches floppy diskette. This was intended to protect the disk from accidental damage by enclosing it in a tougher plastic casing, but did not gain wide acceptance due to the additional cost and compatibility concerns. Such drives would also inconveniently require bare disks to be manually inserted into an openable caddy before use. Ultra-density optical and universal media disk use optical disk cartridges. There were also some early CD-ROM drives for desktop PCs in which its tray loading mechanism will eject slightly and user has to pull out the tray manually to load CD, similar to the tray ejecting method used in internal optical disk drives of modern laptops and modern external slim portable optical disk drives. Like the top-loading mechanism, they have spring-loaded ball bearings on the spindle. Computer interfaces. Most internal drives for personal computers, servers and workstations are designed to fit in a standard 5.25 inches drive bay and connect to their host via an ATA or SATA interface. Additionally, there may be digital and analog outputs for audio. The outputs may be connected via a header cable to the sound card or the motherboard. At one time, computer software resembling CD players controlled playback of the CD. Today the information is extracted from the disk as data, to be played back or converted to other file formats. External drives usually have USB or FireWire interfaces. Some portable versions for laptops power themselves from batteries or directly from their interface bus. Drives with SCSI interface were made, but they are less common and tend to be more expensive, because of the cost of their interface chipsets, more complex SCSI connectors, and small volume of sales. When the optical disk drive was first developed, it was not easy to add to computer systems. Some computers such as the IBM PS/2 were standardizing on the 3.5 inches floppy and 3.5 hard disk, and did not include a place for a large internal device. Also IBM PCs and clones at first only included a single ATA drive interface, which by the time the CD-ROM was introduced, was already being used to support two hard drives. Early laptops simply had no built-in high-speed interface for supporting an external storage device. This was solved through several techniques. Early sound cards could include a CD-ROM drive interface. Initially, such interfaces were proprietary to each CD-ROM manufacturer. A sound card could often have 2 or 3 different interfaces. A parallel port external drive was developed that connected between a printer and the computer. This was slow but an option for laptops. A PCMCIA optical drive interface was also developed for laptops. A SCSI card could be installed in desktop PCs for an external SCSI drive enclosure, though SCSI was typically much more expensive than other options. Internal mechanism of a drive. The DVD-ROM drive in the photo is shown right side up. The disk would sit on top of it. The laser and optical system scans the underside of the disk. With reference to the photo, just to the right of image center is the disk spin motor, a gray cylinder, with its gray centering hub and black resilient drive ring on top. There is a disc-shaped round clamp, loosely held inside the cover and free to rotate. It's not in the photo. After the disc tray stops moving inward, as the motor and its attached parts rise, a magnet near the top of the rotating assembly contacts and strongly attracts the clamp to hold and center the disc. This motor has an external rotor every visible part of it spins. The grey metal chassis is shock-mounted at its four corners to reduce sensitivity to external shocks, and to reduce drive noise from residual imbalance when running fast. The soft shock mount grommets are just below the brass-colored washers at the four corners. Running through those grommets are screws to fasten them to the black plastic frame that's underneath. Two parallel precision guide rods that run between upper left and lower right in the photo carry the sled, the moving optical read-write head. As shown, this sled is close to, or at the position where it reads or writes at the edge of the disc. A dark gray disc with two holes on opposite sides has a blue lens surrounded by silver-colored metal. This is the lens that's closest to the disc. It serves to both read and write by focusing the laser light to a very small spot. Under the disc is an ingenious actuator comprising permanent magnets and coils that move the lens up and down to maintain focus on the data layer. As well, the actuator moves the lens slightly toward and away from the spin motor spindle to keep the spot on track. Both focus and tracking are relatively quite fast and very precise. These servos are comparatively wideband. To select tracks as well as advancing the sled during continuous read or write operations, a motor rotates a coarse pitch lead screw to move the sled throughout its total travel range. The motor, itself, is the grey cylinder just to the left of the most distant shock mount. Its shaft is parallel to the support rods. The lead screw is the rod with evenly spaced darker details. These are the helical groove that engages a pin on the sled. The irregular orange material is flexible etched copper foil supported by thin sheet plastic. These are flexible printed circuits that connect everything to the electronics. Compatibility: most optical drives are backwards compatible with their ancestors up to CD, although this is not required by standards. Compared to a CD's 1.2 ohm layer of polycarbonate, a DVD's laser beam only has to penetrate 0.6 ohm in order to reach the recording surface. This allows a DVD drive to focus the beam on a smaller spot size and to read smaller pits. DVD lens supports a different focus for CD or DVD media with same laser. With the newer Blu-ray disc drives, the laser only has to penetrate 0.1 ohm of material. Thus the optical assembly would normally have to have an even greater focus range. In practice, the Blu-ray optical system is separate from the DVD-CD system. Recording performance: during the times of CD writer drives, they are often marked with 3 different speed ratings. In these cases, the first speed is for write-once operations, the second speed for rewrite operations, and the last speed for read-only operations. For example, a 40A, 48A, CD writer drive is capable of writing to CD-A media at speed of 40A, writing to CD-RW media at speed of 12A, and reading from a CD-ROM media at speed of 48A. During the times of combo drives, an additional speed rating is designated for DVD-ROM media reading operations. In the late 1990s, buffer underruns became a very common problem as high-speed CD recorders began to appear in home and office computers, which for a variety of reasons often could not muster the I/O performance to keep the data stream to the recorder steadily fed. The recorder, should it run short, would be forced to halt the recording process, leaving a truncated track that usually renders the disc useless. In response, manufacturers of CD recorders began shipping drives with buffer underrun protection. These can suspend and resume the recording process in such a way that the gap the stoppage produces can be dealt with by the error-correcting logic built into CD players and CD-ROM drives. The first of these drives were rated at 12A and 16A. While drives are burning DVD plus R, DVD plus RW and all Blu-ray formats, they do not require any such error-correcting recovery as the recorder is able to place the new data exactly on the end of the suspended write, effectively producing a continuous track. Although later interfaces were able to stream data at the required speed, Many drives now write in a zoned constant linear velocity. This means that the drive has to temporarily suspend the write operation while it changes speed and then recommence it once the new speed is attained. This is handled in the same manner as a buffer underrun. Recording schemes. CD recording on personal computers was originally a batch-oriented task in that it required specialized authoring software to create an image of the data to record, and to record it to disk in the one session. This was acceptable for archival purposes, but limited the general convenience of CDR and CDRW disks as a removable storage medium. Packet writing is a scheme in which the recorder writes incrementally to disk in short bursts, or packets. Sequential packet writing fills the disk with packets from bottom up. To make it readable in CD-ROM and DVD-ROM drives, the disk can be closed at any time by writing a final table of contents to the start of the disk. Thereafter, the disk cannot be packet written any further. Packet writing, together with support from the operating system and a file system like UDF, can be used to mimic random write access as in media like flash memory and magnetic disks. Fixed-length packet writing divides up the disk into padded, fixed-size packets. The padding reduces the capacity of the disk, but allows the recorder to start and stop recording on an individual packet without affecting its neighbors. These resemble the block-writable access offered by magnetic media closely enough that many conventional file systems will work as is. Such disks, however, are not readable in most CD-ROM and DVD-ROM drives or on most operating systems without additional third-party drivers. The division into packets is not as reliable as it may seem as CDR-W, and DVD-R-W drives can only locate data to within a data block. Although generous gaps are left between blocks, the drive nevertheless can occasionally either destroy some existing data or even render the disk unreadable. The DVD plus RW disk format eliminates this unreliability by embedding more accurate timing hints in the data groove of the disk and allowing individual data blocks to be replaced without affecting backwards compatibility. The format itself was designed to deal with discontinuous recording because it was expected to be widely used in digital video recorders. Many such DVRs use variable rate video compression schemes which require them to record in short bursts. Some allow simultaneous playback and recording by alternating quickly between recording to the tail of the disk whilst reading from elsewhere. The Blu-ray disc system also encompasses this technology. Mount Rainier aims to make packet-written CD-RW and DVD plus RW discs as convenient to users that have removable magnetic media by having the firmware format new discs in the background and manage media defects. As of February 2007, support for Mount Rainier is natively supported in Windows Vista. All previous versions of Windows require a third-party solution, as does Mac OS X, record a unique identifier, owing to pressure from the music industry, as represented by the IFPI and IAA. Philips developed the recorder identification code to allow media to be uniquely associated with the recorder that has written it. This standard is contained in the Rainbow books. The RID code consists of a supplier code, a model number and the unique ID of the recorder. Quoting Philips, the RID enables a trace for each disk back to the exact machine on which it was made using coded information in the recording itself. The use of the RID code is mandatory. Although the RID was introduced for music and video industry purposes, the RID is included on every disk written by every drive, including data and backup disks. The value of the RID is questionable as it is impossible to locate any individual recorder due to there being no database. Source Identification Code. The Source Identification Code is an 8-character supplier code that is placed on optical discs by the manufacturer. The SID identifies not only manufacturer, but also the individual factory and machine that produced the disc. According to Philips, the administrator of the SID codes, the SID code provides an optical disc production facility with the means to identify all discs mastered and/or replicated in its plant, including the specific laser beam recorder signal processor or mold that produced a particular stamp or disc. Use of RID and SID together in forensics. The standard use of RID and SID mean that each disc written contains a record of the machine that produced a disc, and which drive wrote it. This combined knowledge may be very useful to law enforcement, to investigative agencies, and to private and/or corporate investigators. See also: References. External links: How CDs work at How Stuff Works, How CD burners work at How Stuff Works, Understanding CDR and CDRW, CD Recordable FAQ, CD Blu-ray News and Reviews, Why Audio CDR discs Won't Always Play, How to Fix a Faulty CD Burner Driver, an IDE OD and SATA OD. Both are designed for laptops. An IDE OD. It is 5.25-inch in form factor. A SATA OD. It is 5.25-inch in form factor.